Our objective here is to try to identify just what the performance limits are for each. The question is, what is the difference in the principles of design? What are the performance limits for each of those two pipes?
Recognized as a leading test facility in North America for pipe and water research, Utah State University was selected to perform specific tests on rigid and flexible pipe. The objective was to observe the structural performance and performance limits of rigid and flexible pipe when buried under very high soil cover. As an international authority on soil structure interaction mechanics, Dr. Reynold Watkins is an instructor at the Piping System Institute at Utah State University. Dr. Owen K. Shoup is a professor of mechanical engineering and a member of USU's Buried Structures Research Team. Under the direction of Dr. Watkins and Dr. Shoup, tests were conducted in a 6-foot by 6-foot test cell with 4 loading beams and 16 hydraulic cylinders. A compacted bedding was prepared. Test pipe was laid in place with the balance of the soil compacted in layers to a height of approximately 20 inches above the pipe. Vertical soil loads up to 100 feet were then simulated. Test 1 and 2 were performed using fine sand with 20% silt to simulate marginal backfill soil conditions. Both tests followed identical procedures. Soil was placed in 8-inch lifts and compacted to an average density of 84%. This would represent, at best, marginal installation. A level bedding was prepared. The Class 3 reinforced concrete pipe was then set in place. Soil was shovel sliced under the haunches and compacted. Soil moisture and soil densities were measured and recorded. After the final layer of soil was compacted and tested, the steel plate was set in place to uniformly distribute vertical load. The 4 sets of loading beams and hydraulic cylinders were locked in place. As the vertical soil pressure increased, the performance of the concrete pipe was measured and observed for signs of distress. When the vertical soil pressure reached approximately 24 feet of soil cover, the concrete pipe developed a 1/100th of an inch crack at 12 and 6 o'clock.
Pretty small. Okay, the vertical now is 17.9015.
The yellow arrow highlights the crack.
The cement's starting to chip away a little bit. The sand's starting to fall through a little. 600 psi. Okay, the cement's starting to chip away. 900. Loud cracking. This is starting to fall apart. 1,000 psi. Well, now we're getting big chunks of cement falling. There's 1,200, 1,300, 1,400, 1,500, 1,600, 1,700. There's 1,800 psi.
The pipe did not collapse, but would leak. After the completion of Test 1, the soil was carefully removed and the pipe inspected.
You can see the crack going along the top.
Identical test procedures were used in Test 2. An 18-inch ultra-rib PVC pipe was installed.
With the pipe now in place, we're in the process of compacting soil on the sides in lifts in the same way that we did with the rigid pipe. We will continue to fill it and then load it and then note what sort of performance that we get from it when the equivalent soil height is raised to maybe 100 feet.
When the vertical soil pressure reached approximately 24 feet of soil cover.
Okay, John, we're reading the vertical, and we're reading 16.063.
The ring deflection was measured at 8.7%. As the load increased, so did the deflection of the ultra-rib PVC pipe.
500. Now it's 600 psi, 900 psi. Now at 1,000 psi, 1,200 psi, 1,300 psi, 1,400 psi, 1,500.
However, at no time did the ultra-rib show signs of structural distress. At 100 feet of cover, deflection was 31%.
psi.
Again, the soil was carefully removed and the pipe scrutinized.
Went down 7 inches about.
Rebounding to about 95% of its original shape, the ultra-rib pipe showed no visible signs of distress. As the ultra-rib was lifted from the cell, there was an obvious pipe imprint in the soil, indicating that the bedding material had properly located between the ribs in the haunching zone. In Test 3, ultra-rib was installed in 3/4-inch stone to simulate good backfill conditions. The same procedures were followed as in Tests 1 and 2. A level bedding was prepared and compacted to about 90% density by a vibroplate in 18-inch lifts. As the vertical soil pressure was increased, the vertical ring deflection was measured.
We're reading the vertical, 17.518, 17.379, 17.262, 17.128.
A fourth test was conducted to measure the effects of incorporating a T-fitting and 1 foot of broken ribs on the ultra-rib pipe. Buried in 3/4-inch crushed stone, the same procedures were again followed as in Test 3. These tests were conducted under the direction and supervision of the Buried Structures Laboratory at Utah State University. The contribution made by Dr. Reynold Watkins and Dr. Owen K. Shoup will assist pipeline design engineers to understand the performance limits of rigid and flexible pipe, as well as the conditions under which they can each perform successfully. In Test 1, at 24 feet of cover, the rigid pipe developed a 1/100th of an inch crack. As the soil cover increased, ultimately reaching 100 feet, wide cracks developed in the concrete pipe at 12, 3, 6, and 9 o'clock. The result was a severely deformed pipe. In Test 2, at 24 feet of soil cover, in marginal backfill, the flexible pipe ring deflection was measured at 8.7%. At 100 feet, vertical ring deflection measured 31%. In Test 3, ultra-rib ring deflection at 30 feet of cover with good backfill was approximately 0.5%. At 100 feet, ring deflection was 2.7%. In Test 4, ring deflection at 30 feet was approximately 0.5% in good backfill. At 100 feet, ring deflection was measured at under 2.9%. Conclusion: Tests 1 and 2 show how rigid and flexible pipes behave differently under identical soil conditions and loads. Rigid pipe is designed to resist soil pressure. Therefore, its performance is measured by its ability to withstand longitudinal cracking. Concrete reacts to excessive load by cracking, permitting infiltration. In comparison, flexible pipe derives its soil load carrying capacity from its flexibility. Under load, ultra-rib is designed to transfer vertical load to the surrounding soil. As witnessed in Test 2, ultra-rib transferred the 100 feet of soil load to the marginal backfill, resulting in a vertical ring deflection of 31%. In Test 3 and 4, where good backfill conditions were simulated with common 3/4 inch crushed stone, ultra-rib's deflection was less than 3% when subjected to the same load. In all three examples, the ultra-rib pipe retained its integrity without breakage.
So that establishes then the performance limits for the flexible pipe, which in the case of this ultra-rib pipe would be a ring deflection. And then it would be up to the engineer to determine what ring deflection would be acceptable for him, because we must note that the pipe still serves as a conduit.
The procedure we followed on the second test of the flexible pipe was to try to test a good pipe situation where the pipe would be filled in a typical manner.
What happened to the pipe? Except that it deflected 2.8%.
Not very much.
This would seem to indicate then that a flexible pipe can be used under very high fills if the side fill support is adequate.